Let's tackle a mixture problem where we compute partial pressures for each of the components of our mixture and figure out the total enthalpy change for the entire mixture. So imagine that we're given 22 kilograms of ideal gas composed by mole of 75% oxygen and 25% water. We're also told that there's a fixed gas pressure of 4.0 bar total, but we go between an initial temperature of 300 Kelvin and a final temperature of 350 Kelvin. The first step with any of these mixture problems should be to construct your table. I'm going to assume you can do this if you watched the first video, so we have a table for oxygen and water, and I'm just going to fill in all the values at once. Okay, so I did that. Please review your lecture notes and other videos if you need help on this step. We're going to use some of that information, maybe not all of it, to compute the partial pressures and the enthalpy change. Let's start with partial pressure. It's actually pretty easy to do, especially with a mixture consisting only of two components. So we know that the total pressure is 4 bar. The partial pressures are just these Y values, the molar fractions, times the total pressure. So the pressure for oxygen is YO2 times the total pressure. So that's just 0.75 times 4 bar. Well, that tells us that the partial pressure for oxygen is 3 bars. So let's record that over to the left. And now we need to figure out the partial pressure of water. Well, we can either multiply 0.25 by 4 bar to get 1 bar, or we can see that the two partial pressures have to add up to 4 bar. We know that the partial pressure of oxygen is 3 bar. Either way, you see that the partial pressure of water has to be 1 bar. Let's write 1 bar to the left, and now we'll erase all this other stuff. Okay. Now we want to figure out the enthalpy change in going from 300 Kelvin to 350 Kelvin. Well, that's tough enough to figure out just if you have a pure substance, so you need to take some care doing this with a mixture. The key is understanding how to use these delta barred quantities given in your lecture notes. So for example, delta H bar you can construct this way, and I'll write out the full expression and then explain it. The idea is that delta H bar, which is the molar enthalpy change, is just going to be the sum for each of the two components, oxygen and water, of Y, the molar fraction, times the change in barred enthalpy for each substance. So you can see I've written subscripts to try to indicate this, although there's a lot of subscripts to follow. But basically delta H bar is YO2 times now H bar O2 final minus H bar O2 initial, and then plus the same quantities now for water. So how do we figure any of these out? Well, the nice thing is the H bar quantities are actually given in a table in the back of your book. So if you go through under the assumption you're dealing with an ideal gas, you can find H bar values certainly for oxygen, water, a few other molecules that are very common, and you can just look those up as a function of temperature. Well, that's nice. We know the two temperatures, 350 and 300, so if we look up all of those values in the table in the back of the book, we'll find all the values that I just entered in on the left. So we have all the initial values for both oxygen and water, and the final values, again, for oxygen and water. So let's plug everything into the expression for delta H bar. We do that, we have the Y values, that's just 0.75 for oxygen, 0.25 for water, and we put in all the differences in molar enthalpy. Okay, simplify this a little bit, we get the delta H bar is 1107.75 kilojoules per kilomole plus 421.5 kilojoules per kilomole. Add those together, we get a value of 1529.25 kilojoules per kilomole. Now that's not the total enthalpy change. That's obviously a molar enthalpy, we're still in units of kilojoules per kilomole. So how do we get to delta big H? We would know how to do it if we were dealing with specific enthalpy, namely enthalpy per unit mass, but here we're in enthalpy per unit mole. That must mean that we need to multiply by the total number of moles, little n. So delta big H equals little n delta H bar. Okay, how do we figure out little n? Well, the nice thing is the number of moles is just the mass that we have divided by the molecular weight. So little m is the total mass of substance that we have, big M is the molecular weight of the substance, and we know both of those. We know, we're given in the problem, that we have 22 kilograms of ideal gas. Big M, I actually had to figure out on that table, but remember that's just the sum of all the little m's, so it's 28.505 kilograms per kilomole down there at the bottom. So we can plug that in and solve for n. It'll just be 22 divided by 28.505. That'll give us units of kilomoles, and sure enough we have a little less than 1 kilomole. We've got 0.7718 kilomoles. So now if we want to figure out delta big H, we just need to multiply 0.7718 times the value we just found for delta H bar. So we do that, and now we get our final answer that delta big H is 1180 kilojoules. So that's the total change in enthalpy associated with taking this mixture from 300 Kelvin to 350 Kelvin. Now you can do all of these calculations on a per mass basis too. You should look in your lecture notes. It gives the page number in the book where you can actually find the per mass formulae. At this point, for mixtures, it's honestly probably about as easy to use the barred quantities, the molar quantities, but whichever you prefer is fine with me as long as you can get to the same correct answer.